My name is Tom Turner. I look after the Hub core project on automated dry fibre preforming. And I'm just going to give a very brief overview of one of the areas of development, which is in the digitalization of composites manufacturing. We think the developments I'll talk about today will have benefits both for automated dry fibre placement, which is the focus of this core project, but also in terms of other automated composites manufacturing processes. So, by way of introduction, automated deposition technologies have been around for quite a long time, and they made a lot of promises when they were first introduced in terms of increases in rate, the ability to remove hand labour and have lights out manufacturing, cost reduction as a result, and they basically promised to turn composites manufacturing into a sort of information-driven high-tech manufacturing process rather than the hand labor-driven process it was before. And what we can see even now, many years later, is that AFP hasn't really delivered on a lot of those promises. There's still a lot of work needed, and that's no surprise because these are really complex processes, complex materials interacting in a non-obvious way with some very complex manufacturing hardware. So what we see at the moment is that there's lots of industrial efforts to commercialize new processes and to develop existing processes through incremental changes. But one of the problems is that there's little consensus on the approach. There's lots of different people doing their own thing. There's little standardization. And so the developments we're seeing in this area tend to be, small and incremental. Of course, also alongside that, we've got lots of stuff going on in the wider area of manufacturing. We've got a lot of the stuff driven by the advances in computational science and engineering. So Industry 4, developments in CAE software analysis routes and concurrent engineering. We've got all this stuff happening. A lot of it is struggling to find its way into composite manufacturing. So what's the scope of the University of Nottingham part of this core project? Well, we wanted to do something that looks at the process in a fundamental way, TRL 1 to 3, next generation stuff rather than incremental changes. And we wanted to develop knowledge and ideas that were process and material independent, with a sort of focus on low-cost future materials in mind. So moving to that in a future generation of these technologies. We know that there are some gaps in our understanding of material behavior, particularly during the deposition process, and that we need to have better understanding to sort of unlock the potential of these processes, and particularly for dry fiber, really to exploit the potential cost and process flexibility advantages which aren't really exploited at the moment. And the thing I want to talk about today is how we've made some progress in facilitating a digital twin for composites manufacturing. So that's the focus of this little talk today. Well, here you go. This will teach you for putting a slide animation in when it's not supported. So what I was trying to show here is that the normal way of doing things is that we take a part design over on the left-hand side in our CAE software, and we do some post-processing, typically in a sort of third-party CAE add-on software. And what that means is that there's a disconnect between the design data and the hardware that we're using to manufacture the part. So if you're writing a document in Word, you can make changes very easily until you send it to the printer. And when you've printed it, the printer driver has changed the language that you're using to describe the structure of the part, or the document in this case, and so you've broken that link. So if we're going to exploit some of these Industry 4 type advances that come with a digital twin type approach, we need to have a way of describing the geometry of the composite part as well as the machine control, so that we can have this bi-directional data exchange. And there's lots of problem areas which are shown here, and lots of work is still needed to be done. This is not an easy problem to solve by any means. So what we've tried to do is come up with a data storage approach as really the key sort of enabler for developing some of these technologies. So we've come up with an approach where the structure of the data matches the structure of the parts. So parts are made up of plies, plies are made up of courses, courses are made up of toes, and those individual toes might have things happening along their length. And critically, the digital twin needs to comprise all parts that we've ever made. So we've got our part 0, which is our design part, what we want to make, and then we've got all the parts we make after, and we need to store them all in a unified way. And digital twin is talked about a lot. Often when people say digital twin, they really mean digital model. So it's great to have a model of a process in the same way as it's great to have a model of a part. But the key thing about a digital twin is that the data exchange is automated. So you're able to, in real time, extract information from your physical object and apply it to your digital object and vice versa. And that information exchange can happen in real time, or it can happen asynchronously at any other time. So we're going for this bottom option here, a full digital twin with automated data exchange. So what have we done? Well, we've made a file type based on the HDF5 file format, which is a bit like a whole file structure within a single file. And it enables lots of different data types. It stores lots of different types of data, enables us to put both the part data and the manufacturing data in the same file, and to have this multi-level categorization. So from the part at the top down to ply level, course, toe, and position within the toe. And once we've got this data, what it allows us to do is compare the design part with the real part, which then opens up a lot of opportunities. So we can do things like real-time control, where we can take data off the machine, run a simulation, and then come back and drive the machine either for what it's doing right now, or what it will do in a moment. Or if something goes wrong, we can run an analysis, update the behavior of the machine in future steps. So as I said, HDF5 and this sort of file data storage methodology sits at the center of what we're trying to do. So we're storing the part design data and the metadata about the part behavior. So if we've got a field-based orientation distribution, we would want to include that in the HDF5 file. Alongside this work, as you can see on the top right, we're developing a virtual simulation of the machine. Once we've done that, and there's no barrier between the real hardware and the virtual hardware, we can do things like overlay process data on the virtual machine data. So we can display temperatures, speeds, defects in real time on our virtual twin of the real process, which, you know, some of these things are quite difficult to see on the real process hardware. And obviously we can run that simulation at any time, alongside or afterwards. We can also store all the in-process data that we're getting from the machine in a way that allows us to compare it with what we expected to see when we design the part. So the key thing is really this removal of the barrier between the virtual and the real. So where are we in terms of implementation? Well, we're developing a test rig which is fairly simple by sort of AFP machine standards. There's a real focus on data acquisition so that we can prove out some of these ideas and show that we can capture this data in real time and reuse it. So we're doing things like storing 6 degree of freedom load cell data from the head and using it to adjust process parameters in real time. We're storing temperatures and using them to make model-based control processes for the heating of the binder, for instance. And in the future, what we hope to do is to have more of a real-time, well, to basically move more of the machine control from these upfront process control methodologies to a real-time process control methodology. So by way of conclusion, this is the final slide. What we're able to do if we can implement some of these ideas and prove them out on our test rig. Well, I've split this into two. we can do dynamic, real-time, physics-based process control. So rather than here's what we thought would happen, here's the way we thought the machine or the material would behave, we can take real process data and use models of material and machine behavior to update the process in real time, course by course, or layer by layer. So we can do things like recording temperature history and updating, the nth layer based on the n-1 layer behavior, or that data we've got about that layer. And a key other sort of thing that we open up with this is after our preforming, we then got a full digital model of the structure that we've made. So we can do things like in-process quality control, where we can store data about how the preform has turned out. We can do downstream flow simulations based on a real structure rather than the model that we came up with at the beginning. And we also enable things like machine learning, so that we can feed all the data that we've got from the preforms that we've made into a machine learning algorithm and start to influence future preforms that we're going to make. So lots of opportunities, lots of work still to be done, but I hope to be able to update you on this at some point in the future. Thanks very much. That's everything from me.